In this lecture, we will discuss static electricity, what causes it, and electrostatic forces, or Coulomb's law. The effects of electric charge were first observed as static electricity by Ben Franklin. After being rubbed on a piece of fur, an amber rod acquired a charge that would attract small objects like pieces of paper. Ben Franklin was very curious about this, so he designed a few experiments. He found that charging both amber and glass rods proved that there were two types of electric charge, positive and negative. Ben Franklin knew nothing about the atomic structure of an atom. Electrons had not been discovered yet, so he attributed these charges as the material either having an electric property, a fluid, or not. And he called them positive if they had the electric fluid, and negative if the electric fluid was absent. He also discovered that like charges repelled and that opposite charges attracted. All electrons have exactly the same charge. The charge on a proton has the same magnitude but opposite sign. The charge of an electron, E, is negative 1.6 times 10 to the negative 19th coulombs. A proton has a charge of positive 1.6 times 10 to the negative 19th coulombs. Coulombs will be the unit we use to measure charge. Electrons in an atom are in a cloud surrounding the nucleus. The protons are in the nucleus and are positively charged. If you've ever studied the periodic chart, you know that if an atom has 3 electrons, it also has 3 protons. If this were not the case, then the electrons, which are relatively very far from the nucleus, would not stay intact and in their electron clouds. They would leave the atom and the atom would fall apart. There are 3 negative electrons and 3 positive protons because opposite charges attract. And if you have 3 electrons, you need to have 3 protons to attract and keep all the electrons attached and in their orbital cloud surrounding the nucleus. So what is really happening when we build up a static charge? When an amber rod is rubbed with fur, some of the electrons on the atoms in the fur are transferred to the amber. So the amber gains a certain number of electrons and negatively charged. At the very same time, the fur has lost that number of electrons and has gained an equal amount of positive charge. Positive charge indicates that you have lost electrons. Negative charge indicates that you have gained electrons. Ben Franklin realized that electric charge was conserved in this manner, that if the amber gained 2 electrons, then it had the charge, the total charge of 2 electrons. But at the very same time, the fur had a positive charge equal to that of 2 electrons. That's because Ben Franklin realized that electric charge was quantized. If the amber gains 1 electron of charge, then it has a charge of negative 1.6 times 10 to the negative 19 coulombs. If the fur loses 1 electron, it now has a positive charge of positive 1.6 times 10 to the negative 19 coulombs. Ions work this way as well. In chemistry, you've learned about positive and negative ions. Remember that an atom that has lost an electron is called positively charged, or a positive ion. Atoms that have gained electrons are negatively charged, or negative ions. You can charge an object that is neutral without even touching it. How does that work? Well, first of all, a neutral object is an object that has an equally distributed number of positive and negative charges. There's no, excess of electrons or loss of electrons on the surface. So imagine a balloon. The balloon only has a neutral charge. If you bring a positively charged rod near it, the positive charge will cause the atoms to rotate such that all the negative sides of the atoms are attracted to it. So this induces a negative charge on the surface of the balloon, and the balloon becomes negatively charged and is attracted to the positively charged object. So, in essence, you have induced a charge on the balloon, and you never even touched it. There are materials that conduct electricity easily. These are usually made out of metals that are large atoms. In these large atoms, the electrons in the outer energy levels of the electron clouds are not very tightly bound to the protons because they're so far away from them. So if you take a metal wire and you connect it to a voltage source that has a positive and negative terminal, the electrons are going to be attracted to that positive terminal and will start moving freely through the metal. An insulator, on the other hand, is a material whose electrons seldom move from atom to atom because the insulators are nonmetals and the atoms are very tightly bound to it. A conductor carries an excess charge, but the excess charge is distributed only on the surface of the conductor. There is no charge on the interior. Semiconductors have properties intermediate between conductors and insulators. Their properties change with their chemical composition. If you dope silicon with germanium, it's a conductor. Photoconductive materials become conductors only when certain frequencies of light shine on them. So we've been talking about charges repulsing each other or attracting each other. How do we calculate the force of attraction or repulsion? We do that using Coulomb's law. Coulomb's law gives us the force between two charges. The force is equal to the Coulomb's constant K times the charge of the first particle times the charge of the second particle divided by the distance squared. Coulomb's constant K is 8.99 times 10 to the 9 newtons times meter squared divided by Coulomb squared. The force is along a line connecting the charges, and it will be attractive if the charges are opposite and a negative number, and repulsive if the charges are like a positive number. So in this example, we see two positive charges. The force is repulsive, indicated by the arrows acting in opposite directions. Notice that the arrows are exactly the same length because the force for both of them is calculated using Coulomb's law. Even if Q1 is twice as big as Q2, the force will be equal and opposite due to Newton's third law. Also notice the notation used in the book. F21 indicates the force on 2 by particle 1. Example 1. Two electrons are located 4 millimeters apart. What is the electrostatic force exerted by each on the other? We're going to start with Coulomb's law. We're going to make sure that Q1 and Q2 are in coulombs and that R is in meters. Substituting into the equation, we'll substitute in 8.99 e to the 9 newtons meter squared over coulombs for K. times the charge of each electron, which gives us negative 1.6 e to the negative 19 coulombs squared. And then we'll divide that by the distance in meters, 0.004 meters, and square it. That will give us 1.4 times 10 to the negative 23 newtons. Coulomb's law is an inverse square law with distance. If you double the distance r, the inverse square will happen to the force, so it will be 1/4 as much. If you cut the distance in half, then the electrostatic force will be 4 times as much. And finally, remember that force is a vector. When you have more than one force acting on an object, you have to add the forces using vector addition. So, for example, if I wanted to find the net electrostatic force on Q1 by Q2, Q3, and Q4, I would have to find the force due to Q1 using Coulomb's law and then resolve it into its x and y components. I would have to find the force due to Q2 using Coulomb's law and then resolve it into its x and y components. And likewise with the force due to the third charge. Then I would add all the x's and add all the y's to get the x and y component of the total force F1. And then I could use Pythagorean theorem and tan theta to find the magnitude and direction.